whatever you need, we'll help. We will. And if we can't, we'll tell you we can't. But I mean, it won't be because we don't want to. It's because we might have the same problem you do. You know, I don't know.
Congratulations on the purchase of V212. We are watching.
We have to take a field trip. We need to go to Detroit. We were driven to a super secret location to peek at some of the coolest cars in General Motors' extensive heritage collection.
It smells clean.
Oh. Thank you so much. That's been amazing. Appreciate all of the time.
Absolutely, but you're not done yet.
Well, hopefully you guys had a great tour of some of the heritage of electrification and propulsion at GM with Adam and Kevin. And you're going to look and take a look at what the future is, which is really exciting. So hopefully you have a great day doing that.
All right.
I'm sure Billy was really excited about the Sun Racer.
Yeah.
He was like a kid in a candy store.
That was a dream come true.
Wasn't that something? It was, well, if you look at the shape of EV1 and you look at the teardrop.
Side by side,
it's, the aerodynamics was happening. Yeah.
The impact was right next to it and you're like, we can see that.
Yeah, oh yeah, no, I know.
Yeah,
it's pretty fun stuff.
Well, yeah, it was amazing in the Heritage Center with all those guys, and just you could feel the raw emotion that they had.
Yeah, it's a great history.
Well, Mark, thank you so much for having us out. This has been spectacular. It's absolutely not what we expected, but it has gone, we couldn't expect everything that you've done and the help you're lending to the restoration. But while we're here, we kind of want to ask some questions, if that's all right.
Yeah,
so
absolutely.
Billy's got one to fire off. We'll get through that real quick, and then we can talk a little bit more maybe about the future and some of the other things really exciting going on.
Yeah, excellent.
Yeah, so we know the auction was kind of unexpected.
Yeah.
But what did you think when you saw what happened?
I don't know why I have a sort of a fascination with EV1s. I do know why, actually, because my dad played a big part in doing it. But I always look at things like where they found one in a parking structure, and I was like, man, I wonder if we could get that, you know. But this one was like, oh my gosh, there's an auction from a place where it was sitting, right? And so I watched your show, and you detailed how you did it, and then I was like one of the coolest moments in the show for me, because I'd never seen it, was the actual sheet of paper that went with those cars we donated, which I didn't know that. It says, we will not ever help you get one back on the road. We won't help you do this. We won't help you do this. Like, wow, this is a company that wasn't really fired up to continue anything around this. We're going to have to scrap them, right? And so it was, I get it, you know, from a legal standpoint, but that was really what drew me into it. And so that was pretty awesome. Yeah, and then I couldn't stop watching the episodes.
Yeah.
So it was great.
Yeah, I think we're just as drawn to this car as you are.
Yeah.
And we're so happy that we get to bring this one into the future.
Yeah.
And you know, talking about the future, you know, in 10, 20 years from now, when car enthusiasts or anybody's looking back at the EV1, you know, what do you hope they might think about it or understand that they might not understand today?
I think it was more than, you know, there's plenty of people and companies going way back in time that made electric cars, you know, and tried to mass produce them and try to bring them to market and all that stuff. But this one was really commercialized really well. I guess the company put a team of people off-site, and we learned, I mean, of course we learned about batteries. There's 2 generations of batteries with it, obviously. But we also learned about how to manufacture something that had that low of a coefficient of drag and still have it comfortable,
right,
and still have the ride really nice. It was relatively fast, you know, 8 seconds, I think, 0 to 60, roughly. And so all those things together, it was a moonshot on so many, and you know, the inductive charging and the nose. I mean, that was like Delphi and Delco, and that was like, I mean, all those things. I don't think people really know that, and what they see in a movie of different sorts a couple of times was that GM was the evil EV, destroyer. And yes, we were doing it with carb, zero emissions, all that stuff. Of course, we're a regulated industry.
Totally.
But we also knew that people really had interest in something that was really good. And I don't think that spirit's gone away in the EVs we make today. So we're not going to make anything that people don't want per se. It's a great car. It happens to be an EV. So I think that philosophical approach to the car really made a big difference. So it was the timing was not right. I will say that these are long lead programs, and you could talk about propulsion and timing all day, and it's hard to time it right. So it's not just customers only; it's value. It's the whole ecosystem of that we live in from an environmental standpoint. It's all that stuff. So I know based on data, and Bill, you were talking about it, that people have an EV, they don't really want to go back. I didn't want to go to the gas station when it's -10 in Detroit. I don't want to go when it's 120 in California.
Right.
But besides that, it's instant torque. It's it's just so fun to drive, and it's all those things. And I think 4 out of 5 people that have one will never go back, and that's the data. And so I think we have to get the price right now, which we are with things like the Equinox, and the new Bolt that's coming out is under $30,000. That's pretty awesome. And so the charging infrastructure continues to grow every year. And it becomes easier and easier. And so when we get to a point where we have real cars, which we're just doing, that people can have one car, families that have one car for the family, and it can be an EV. And it can have the range, it can have the value, it have the utility, and it's a pretty car, and they're proud of driving it. And that's the win. And so the industry's real close to that. And I could argue we have it in things like the Equinox and everything else we make that's over 300 miles of range. 300 miles of range is huge. Right?
Huge, and it's way more than a car.
Yeah.
For me, it's a power source when my power goes out.
Totally.
It lets me use my electric tools out in the field, in the farm, way from the building.
Yeah.
So
towing capacity. You've got a work truck, and those tow.
They tow.
They tow, and they're just super fun to drive. Yeah.
So we're kind of talking into the future. When you look at the EV1 and GM's honestly vast lineup of current EVs, do you feel like the story now is redemption for the EV1, a continuation, or kind of something else as you're continuing to move the EV programs forward today?
Probably not for a lot of people here we have a relatively young workforce in GM, and especially in the technical fields. So that's exciting. I don't think they know some of the things that happened in the past, but for me personally, I've been here for 40 years and seen it all. It feels really good, and redemption is I don't know if it's redemption, but it's like defiance, and I feel really good about that, because there are people who made a living criticizing GM and EVs. They made a living for years on it. And they said, we don't believe you, you're never gonna follow through. And I said, just watch. And so we'd made the dedicated platforms, we'd have the dedicated cell vertically integrated. We have manufacturing of cells, we know how to do it really well. Those are things we didn't do before, but we're doing it now. And we're not letting off the accelerator on this, we're just not. And so I think it's really going to pay off. It already is, because the cars we have are really good. And so any price range, they're really good cars. So it all starts with the product. Nothing happens until you sell a car. I don't care if it's EV, ICE, or whatever. And if you make bad cars, bad things happen. And so I'm really proud of the cars that we have on EVs. Really proud. So that feels really good.
It feels like GM's not doing it just because of to meet a government standard. It feels like the attitude is GM wants to see this technology succeed. The fact that you're investing, you're building your own battery plants, the research and development, it feels kind of going along that, maybe not redemption, but just proof of concept.
Resilience. Yeah, I think it's resilience and proof of concept. Yeah, for sure. I mean, think about the value doing all those investments that we can deliver to the customer in a really good way with a great car when we get higher energy density at lower cost, and you don't have to carry as much battery. And that's a journey. We're already seeing it. You saw it today with LMR. That's the first like real product out of what we invested in, and that's gonna be great. So we don't have to rely on someone else to do it. That's a big deal.
All right, we're gonna jump. I had one more question. We're gonna pivot from that because I know we're short on time.
You're okay.
And you wanted to talk about something specific that we saw and kind of fell in love with.
Okay.
Everyone has a perception. EV1, that's an electric car. The Volts, the Bolts. You're starting to see some luxury EVs, but there's not really a standout. Then we went into GM EV or GM1, the beautiful new downtown, and saw the Celestiq.
Mm-hmm. That stands out.
That's a car that when you see in person and you see that craftsmanship. So I know we were talking some off camera and you're kind of proud and
very proud.
That's the flagship. And I think because that goes back to the original Cadillac of that was the car. That was the luxury
standard
car.
of the world. Yeah, it was. Yeah, it's a really important car for, we've been working on sort of the redefinition of Cadillac for probably 4 or 5 years. And we said that it's going to be the tip of our electric spear. And that is the Celestiq. We haven't done a handmade car since 1957, which was the Eldorado Brougham, and it had a stainless steel roof, and it had, a compass in the mirror, and lights that dimmed or it's all that, right? It's like electric windows. It even came with like a bar in the glove box. We didn't do that. Right? We didn't do that right now. But we have things like that in the car that are very special. But the electric piece of it is very special. It's a bespoke pack. It's a one solid casting for the underbody, electric doors, 4-wheel steer, air ride, anti-roll control. I mean, it goes on and on, right? So the software in it and the hardware are works of art. They really are. So, and we picked that. If we weren't committed, I'm not sure we would put ourselves out there with a Cadillac at the very tip of technology to take on all the other luxury brands, right, that are out there with something that they don't have. And it's very American. It's not cheap. It's not supposed to be cheap, but it is the design language of Cadillac for now. And we have a manufacturing slot here at the Tech Center dedicated to a flagship car for Cadillac for the foreseeable future. And so right now it's Celestiq, and there won't be many of those made and on purpose, but what's next will be extraordinary as well.
What do you hope to see for V212? How do you hope this project turns out?
I hope you got what you need, okay, number one. And I know there's things software-wise that we can help you with some of those, but some of those you said are very challenging, and they're made very challenging on purpose. So there couldn't be, all that stuff, right? So we'll do our best to help you with that, but hopefully you got some of the parts. I know there's panels that my eyes lit up when you guys were like, I don't know what we're going to get. I think it was a quarter panel or it was a fender. I can't remember what it was. It was a quarter panel.
The windshield.
Yeah, the windshield.
And the quarter glass.
And the quarter glass.
Unique only to the EV1.
Yeah. So hopefully we got all that. But I really want to see that car. I want to see you both driving that car on the street. It would just be great, right? That's really what I want. And be proud of it. And I know you collect electric cars, but I mean, this is like a lifetime deal for both of you. I hope you feel that way. This is like the challenge of a lifetime.
That's it,
yeah.
Absolutely.
Yeah, which is like, that's cool, right? That's like so cool. That's why I got hooked on it. And I just can't wait for you guys to be able to do that.
So next year when it's ready for Woodward, you'll join us with a Celestiq or whatever the new flagship.
Hopefully the one we got, it's running, so it'd be kind of a cool
We'll bring up one or two of our electric S10s
I'll try and
the
draft.
EV1s.
I'll draft you guys. I'll try and draft you guys. There's not much there to draft, but I'll try and draft you aerodynamically.
Well, there's really not that many EV1s out there, as you know. Most of them are museums or with schools and locked up, and we're calling this one the EV1 for the people.
Oh, are you really?
Yeah, we're gonna get it out
I was
there.
saying, get it out there and drive it.
Yeah.
That's it. Yeah. No, don't hold back. Yeah, that's awesome. I love that.
And we love being able to share, because we were worried there's several buyers that it would have just disappeared again because of the fear and things like that, and the opportunity to show the car, every detail of the car, for people who didn't know, or some of the engineers were almost in tears meeting us because it was their baby coming back.
I know.
It's
It was
insane.
emotional. It was emotional. It was
It's
a big
definitely
deal.
bigger than any one of us, and we understand that.
Very cool. That's so cool, you guys.
And thank you so much, because
Oh,
the help and support.
Whatever you need, we'll help. We will. And if we can't, we'll tell you we can't. But I mean, it won't be because we don't want to. It's because we might have the same problem you do. I don't know. So that's awesome. Yeah.
Thank you. I feel like we're on the path to success, especially when we've got GM kind of behind us, pushing us and cheering us. So
Thank you, Mark, so much.
Thank you guys so much for all you do.
Yeah,
It's
absolutely.
a big deal. It's emotional for me too. My dad's probably looking down on this saying, how good is this, right? Yeah, so it's neat.
Awesome.
Yeah.
Well, all right. There definitely is more, and we are now in a working battery lab. I can't show you getting here because there's a lot of secrets, but we can show you some really cool stuff. And to show us that, I've got Kurt. Kurt, who exactly are you? What do you do? And why do you love batteries?
I'm Kurt, and I joined GM about 2 years ago. I've been in the battery industry for 30 some odd years now.
So your specialty is not necessarily fully in the formulas of battery, but it's how to fit them in a car, how to make them happy and live correctly, more or less, the architecture of a battery.
It's how to get the right battery for the right vehicle.
Okay.
That's really what our job is.
And you've got some cool stuff to show us. So, on camera, this may look like it could be an EV1 battery, but it's not. It is the Gen 2 volt battery, correct? Still that T architecture?
GM really started with EVs with the EV1.
Yeah.
And it kind of looked like this, so that, as you said, with this T shape. Those are lead acid batteries, 12 volt lead acid batteries. I think we had 26 of them. So this one is actually a little bit different from that. There was a gap after EV1 was finished, and then we came out with the Volt. The Volt with a V is in victory.
Yeah.
And that's what this is here. So this is your T shape. You can see the back seat. This goes under the back seat. It's efficient use of space. And this was when we're using lithium ion. And it's really the first time we've had a production plug-in hybrid vehicle. And this is 2009, 2010, somewhere around that time frame where this came out.
Now, this is a water-cooled pack with looking at
It's a
these?
liquid-cooled, our first liquid-cooled pack, because the EV1 was just air-cooled, but this is the water-cooled one.
Starting to add the external, and that allows energy basically to come in and out faster and keep them more stable, correct?
The temperature is really critical because for two reasons. One is safety. You want to keep them at a good temperature. But the other thing is you want them to be uniform temperature because you don't want cells to be aging at different rates.
Right.
You don't want this section getting old first. So you want consistency. Yeah.
You mean like the air cooled where the front battery is the coldest and the rear got all the hot air? It's trying to keep it stable?
Try to keep it stable, exactly.
Now, one thing I'm noticing looking at it, it still looks very brick-like. We've not gone to round cells yet. Like I tore apart a Tesla pack.
Yep.
Some people told me I was an idiot for doing it. I mean, I didn't shove the screwdriver in too far to break the glue lid, but those are all round cells. This looks like a flat module, or are these hiding round cells inside?
They're prismatic cells, but so we don't use cylindrical cells at GM. Tesla's focused on that. There are several other companies that are using cylindrical cells. It's interesting how the market's evolved because you can have pouch cells, prismatic cells, cylindrical cells, and every manufacturer's got their preference for what they use. And you can see when we go back here, this is our current version that are out in the marketplace, which is pouch cells. So these are pouch cells going across, and so this is, I think this is a Lyric pack or something like that, a Lyric optic. So it's one of it's our current generation of vehicles. This is NMC that we're using here. A high nickel cell is what we'd call it. And then the modules that these go into are standard across all of our vehicles. So we've got now 12 different EVs on the road right now, and all of them use the same module, same cell and same module. And then they've got different module configurations. So you can see here, I think this is a 12. Yeah, this is a 12 pack. They can, if you fill this all up. And then the biggest one we do is a 24 pack. It's basically another second level on this. So if you're looking at a Hummer or a Silverado, you can have the double layer.
So it's this and then literally a second one on top.
It's literally a second one. So we've got the same module, and that was a fabulous strategy for us because we could quickly get out a lot of vehicles with a limited amount of development time.
Right, you need the space, so you adjusted it, how you drop the bricks,
exactly,
and pouches in, and boom, ready to go.
No, that's right. So if we take this and then we go over to what we're working on next, so our next generation product is we've got a little demo pack here to show the difference. So this again is our current module with pouch cells in it. So it shows you what that looks like. But what we're doing going forward is we're going to use LMR chemistry, lithium manganese rich, and you'll talk about that later a little bit more. But that's displayed over here. And what we're able to do by going in this direction is we're able to reduce our module count by 75%. We're able to reduce our part count almost in half by going to this large format prismatic cell.
Basically, the things, I did a soapbox on my S10 EV when I was putting it together. I'm like, don't force people to buy them, let the technology, let the car become better and people will want it. This is kind of that next step, is you're reducing repair costs. Replacement batteries are cheaper because instead of everything having its own little thing, it's now a more universal style.
And you can imagine with less parts, you've got less warranty issues. It's gonna there's less stuff to break. But the other thing is the chemistry is really critical here. The chemistry allows this large form factor. The chemistry also gets us this higher energy density than you get with an LFP. So we'll get roughly another 30 to 35% energy density with LMR versus an LFP.
That's like having 1.3 gallons of gas in a 1 gallon container.
Yes.
Not directly at all in energy, physics, or anything. It's just if you magically could put 0.3 more gallons in your 1 gallon gas can, there's so much more science behind it, but I'm trying to make it basic for you.
No, that's right. And then the thing that's also really important as far as a customer perspective is it's roughly the same cost. So you with an LMR, you're going to get that 30% more range in your vehicle, but you're going to get a similar cost. So that's really what we're targeting, is we're trying to drive down costs, because that's really what we need in order to get EV adoption going forward. You got to get the cost lower, and that's what we're working on here.
How well does it charge? Is it able to charge as quick? Is it a little bit slower? Can it be a little bit faster? Is there other limitations, and it's not the battery yet as far as charging?
Yeah. One of the beauties of the LMR chemistry is there's really no trade-offs. And so normally when you come up with a new battery chemistry, it's great in this area, but unfortunately it's really not good in this area. The one drawback we have found with this, it is a really low state of charge, like 10% state of charge. The power that we can pull from it is not as great. The impedance is higher. But it's a very rare case when you're down at around 10% and you're doing 0 to 60 accelerations. That's not our target audience.
It's like your old AA, that your tool turns a little bit slower on the end versus most of your lithium where it hard shuts off. It kind of goes back to that. It tapers to the very end rather than just suddenly dropping off. But again, proper education, you're not going to experience that condition.
And the beauty is that low cost and the high driving range. That's what we're really going for.
That kind of relates into how much does it cost, or how has technology improved to reduce cost per kilowatt hour? Basically, kilowatt is the gas tank of a battery. We're driving cost. That's the goal of it, but how much has that improved over the years?
Yeah, in general, I mean, when you look at Moore's law, you're looking at basically the cost will, or the performance increases every 18 months.
Right.
We're in a different world. This is the chemistry world. And basically, it's on a 10-year cycle. So you're going to double energy density over a 10-year period. Roughly, that's what it's done in the past. When you went from NiCad to nickel metal hydride to lithium ion. That's generally how it's happened. And we've had a really good progression over time when we started with the EV1 and starting with lead acid, went to nickel metal hydride, then lithium ion. The energy density has gone up tremendously over the years. And we keep driving it further up. Although what's interesting here is the energy density per cell is actually a drop down because this is a high nickel versus the LMR. Because what we're doing right now is we're focusing on cost. The biggest thing we're trying to do is drive down cost for the consumer, and that's it. And so we're taking a little bit of a sacrifice on energy density in order to get that better cost. That's what we're doing here with LMR, but we're still able to get the 400-mile driving range, which is really critical here for our trucks.
Are we getting really close to that ceiling of lithium, do you think? There's only so many ways you can max that, so we're now at the point that it's going to take the revolution of slightly new mixes, new compounds, or do you foresee, it's hard to tell the future, but is there maybe something new coming that will absolutely break battery technology to where suddenly we double or triple for the same space?
So I've been going, I'm a battery conference junkie, and I've been going to these for over 20 years now, and I'll still remember in early 2001, 2002, hearing multiple presenters say, we're approaching the limit of lithium-ion batteries. We're not going to get any more energy density out of it. And this came up repeatedly. Every year we get improvements. There's incremental improvements every year. You get a little thinner foil, you get a thinner separator, you add a little bit more nickel. And so every year you're getting this 3-4% increase. And they're little pieces, but adding together, they're significant. And over time you get a bigger increase. So if I were to say we're not going to get any more energy density, that's not going to happen. We see in the future, we can see what's 3, 4, 5 years out, and there's a clear roadmap to improving the energy density. And then at some point, we're going to change that cathode again, like what we did this time, the LMR. The beauty of LMR is we're at the beginning of that cost down curve. So the high nickel's been out now for 20 years. NMC's been around for 20 years now. What LMR now is a huge reduction in nickel. Nickel's the most expensive component in the battery cell. We're getting rid of the nickel, not all of it, and then we're replacing it with manganese, which is cheap, abundant everywhere. So that's the beauty of LMR, and we're just starting down the cost curve. So when NMC first came out, it came down that cost curve over the last 20 years like this, and it's been bottoming out recently. So what we're doing is we're starting here, and now we're going to start coming down that curve.
And you have a battery that is almost as dense.
Exactly, at the starting position.
With the idea, you said battery conference junkies, I'm going to throw a curveball.
Yeah.
Solid state batteries, that's every 12 months to 18 months. It's going to break the battery world. They're ready for production, and you're going to have 10 gigawatts in your hand.
Yeah.
Do you think solid state's practical, or is it still going to be boutique? Is that still decades away? Is there any chance of it actually coming into a car, the magical, perfectly safe solid state?
Yeah, I mean, we're all looking forward to that time where you get this huge improvement in energy density, and solid state is one of those chemistries that are on the roadmap. Is it going to be out next year? No. Is it going to be out 5 years from now? You'll see some prototype vehicles out there. It's not going to be in mass production, and the reason for that is it's going to be prohibitively cost expensive when it comes out. But it's still many years away.
It's just funny, like constantly there's a news article pops up about how it's, you're going to power your phone or your car from your hand, and I keep waiting, and I don't see any solid states here, which means it's still an infant.
So we're in the testing lab right now. We do have an R&D lab, and we do have solid state there. If you went there, you'd see it. So we're testing these, and that's why we know so much about them. That they're not ready yet. We've got to keep doing that. So we're working with many of the leading vendors out there.
Trying to find a way.
Well, trying to find a way. I mean, whether it's solid state or whether there's a bunch of other chemistries we're looking at as well. Solid state is just one of the chemistries we can choose from.
So there's a lot more that the general public doesn't know. So we're nearing potentially the life cycle of lithium, but there's 12 more coming. It's just going to keep getting better. There's kind of one last big battery pack question I feel like I can throw at you. Everyone remembers all the new electric cars and all of them burning down, and they're just catastrophically unsafe. That is an outlier and not generally true, but how has pack safety been improved? How are things changing as we've learned more about more electric cars on the road, how to keep a pack safe, how to keep the catastrophic burn downs from happening.
Yeah.
Where have we seen in GM's path to making the batteries as safe as possible?
Well, I like the way you introduce that because if you read the news, it sounds like there's fires all over the place. But the safety record of EVs is actually much better than ICE vehicles.
Right.
So we really have a good safety record, not just at GM, but the industry as a whole is doing quite well with safety. It's just they get the headline news. But yeah, and over the years, we've learned a lot. I mean, every year we're learning new cases of what could cause a cell to go into thermal runaway. And there's a lot of these use cases that over time you learn and then you build up resistance towards. You build a design that's going to be resistant towards that particular effect. But in general, I can also say that the direction we're going with this large LMR prismatic cell is really it's a nice safe cell.
Yeah.
Now we've got, again, not in this lab, in a neighboring room, we're doing all our battery safety testing. So we'll take individual cells here, we'll put them into thermal runaway, we'll take groups of cells, put them in a thermal runaway, find out what happens. Does that thermal runaway propagate to the neighboring cell, does it not? What kind of materials really prevent that from happening? So there's a huge amount of effort, and even before we do that, there's a lot of modeling work that goes on. So we model all this stuff out to figure out, okay, what's going to work and what's not. Then we actually do the cells, and then you have to do a beginning of life, but you can't stop there because how it will react at the end of life is going to be different than the beginning of life. So you got to cycle these 1,000 times and then do the test again and find out how it's going to perform.
That's what you hear in the background. There's a bunch of machines, I guess, that are just charging and discharging modules and cells all around us. So you test them new, you run them through your 1,000 cycles, and then you go. I think I want to sign up to be the guy to blow up batteries. I don't know that it needs to be scientific, but if I can intentionally be shorting batteries.
Oh, those guys have the most fun. Yeah.
The destructive testing side of things.
Yes.
So.
They do. They have a lot of fun there, and but we try to make it boring for them. We try to make it so there's nothing's going to happen, but they've got to test the limits.
Right.
How far do you have to go till something like that happens? We need to understand that.
So we're talking about making uniform, fewer number of parts, but what is the true scale of these buildings, of the program, when you're trying to move and pivot and take the leadership and be the frontier manufacturer of EVs? We're seeing a big building, but...
Yeah, you're really seeing the result of a lot of work that went into this, because what we do is we start with our R&D facilities. Like this LMR cell that came here, we started work on that 10 years ago in our R&D facilities. That's 10-minute walk this way. We've got the facilities there. Then we built up this other facility called Wallace Center, and that's where we build cells. So these cells were actually built in the Wallace Center, where we build up our prototype full-scale cells. So that LMR work was transferred from that R&D group about two and a half years ago to the Wallace Center, where they started building up cells like this. Then we've got another center, the BCDC, the Battery Cell Development Center. That one is building up large volumes of cells. So we're going to be able to do 0.5 gigawatt hour there. That comes online later this year. So in the future, these cells would be built there. So we've got these two really large facilities, much larger than this here. Right. The Wallace Center is probably 5 times the size of this massive room here. And then the Battery Cell Development Center is another 10x of that. So it's really quite large what we're doing here, and it's a lot of personnel that are working on this, that are doing the basic research. And
if you had to guess, just in battery, rough number, how many people would you guess are part of that program?
Oh boy, it depends on how you define it. It could go anywhere from hundreds to a few thousand. But in starting with the LMR 10 years ago, we started a whole bunch of other things, and there's it comes down like a filter. You're going to start out with 10 different chemistries, and you're going to end up with 1 or 2.
You find the 1 or 2 favorite racehorses early on, and we're betting on these.
And the other ones are thrown out. But that's the job of R&D. You've got to explore the frontiers of what's possible. And so that same team is now exploring solid state and the other things along with solid state. But it's a whole long process here that we're really situated in a position that no other OEM has. We have this R&D capability where we can do pouch cells or coin cells. When we've got our Wallace Center, which will do these large-scale cells, maybe a couple dozen a week type of thing. We've got the BCDC, which will do 0.5 gigawatt hour a year, and then we're the largest of the OEMs battery cell manufacturer at Ultium, so we manufacture the cells as well. So we have tremendous facilities, and all these are located right next to each other. They're all within a short walking distance, so you get a lot of synergies from that. People working together and doing brainstorming together, so it's really, really helpful.
So from my perspective, it feels like GM is positioning itself to be the leader. How does it feel to kind of be one of the members and leading the program of trying to innovate and become the electric car leader?
Yeah, so, I mean, we've come a long way over the last several years. I mean, right now, we actually have the #2 market share in the US in EVs. We've doubled our market share over the last year. We're double our nearest competitor. So we're really staking out a leadership position in the market. And our leadership is convinced that EVs are the future. So when you hear our CEO, Mary, talk about it, EVs are a North Star. It's guiding us in this direction. We don't know exactly when EVs are going to just take off in a massive way, but that's what we're focused on. That's what our group is really trying to enable, is drive down that cost to make them more readily available, so we're going to sell more of these.
I'll say, just as a petrol head, as an outsider looking in, as an enthusiast, I feel like a lot of success is happening because the company hasn't pivoted everything in. You're co-developing ICE, looking at hybrid, plug-in, and full electric, which seems like the no-brainer move, but it finally took a company with vision to actually move everything forward, because we're not at the point that you can dump one cart or not. I know your time's short, so I've got one fun question. I will go home after building a car, wrenching on it all day, and I will stress, did I actually tighten that bolt enough? I've just put an engine together, it's all bolted up, and I'm first start in the morning, and it's like, did I actually torque that rod cap enough? What do you go home from the lab and just kind of wonder, did I do this right? Did I not quite get that? Like, what keeps you up? What just runs around in your brain after hours? What work follows you home?
Yeah, no, earlier in my career, I had the same concerns you did. Did I tighten that bolt, or did I sell the fish that were going to be rotting? That's a longer story in the fish business. But today, the biggest concern that I have is, can we drive down the cost fast enough? Right. Because we know that when customers get in an EV, that they're not going back. We've seen data on this, 85% of EV buyers, their next vehicle is going to be an EV. So once we get them in an EV and they recognize the benefits in terms of performance and safety and a quiet ride and all the benefits that come with it, ease of charging at home, all this stuff is very, very convincing to be as an EV buyer. The thing is that we can't get enough people in the cars right now because the cost is too high. Right. And so what we're doing in our group is, how do we drive that cost down? Because 40%, 30 to 40% of the cost of an EV is the battery. So we've got to be able to drive that cost down of the vehicle. So we're spending our time at work, the majority of it working on that. We've got driving down cost is a big thing. Improving the performance, as in the range and the charge time, is another important metric. And the third one is, how do we localize the supply chain? Those are the three things that we're working on. Yeah. It's the cost, it's the range, it's the charging time. Right. Those are the three things that the customers are really worried about.
So, and I always say, I feel like the perfect customer, like every major city, should be as electric as possible, because how much better would be going downtown and not hearing, again, I love gas cars, I have lots of loud cars, but in a city, not having all the emissions and all the noise would be kind of nice. But a city is almost the hardest spot to regularly charge an EV. So there's so many small pieces to figure, but it feels like, or it's looking like, there's a lot of work being done to actually solve all of those problems.
Oh, absolutely. And I mean, there's other areas like the EV charging network. Yeah. I mean, the building out that's being done there to really enable people to go on the long trips that we all like to do. So there's a lot of work that's being done on this. It's going to really, I mean, the EV transition, it's going to happen, and it's going to be exciting when it really takes off. And it's just a matter of a few more years.
All right. Well, we have a new friend, Andy.
Hey, how's it going?
Very good, very exciting. Still very noisy here. You're still testing.
Yes.
I tried. They wouldn't stop.
The testing continues 24/7.
What do you do here?
I'm a battery engineer at General Motors. I've been working in batteries since 2008, but for the last 2 years, I've been working as Kurt Kelty's business planning manager. So I'm not only doing engineering anymore, I'm working with Kurt on the business and operations side of things and strategy in addition to engineering. So it's another angle, but a lot of fun.
All right, I think your big role here, Kurt went through and fed us the alphabet. LMR, LCBs, LFIPOs, QMSs, and all kinds of things. That's battery chemistry. I know some of those letters, but not all of them. But we don't just start in lithium. We kind of go back. Lead has been our primary battery medium for a century.
Absolutely.
So I think you're here to kind of talk and give us a history
25
lesson.
or 30 years of battery history on this table, and then we've even got a little bit of a glimpse of the future. You were absolutely right that it goes back to lead acid batteries, and in fact, General Motors invented the electrical system for vehicles and the electric vehicle starter, which went back to putting batteries into cars to make them easier for people to drive. And because vehicles have had batteries for lights and starters and things like that since the early 1900s, we've had a battery lab to help make those batteries better, even before there were electric vehicles. So it was pretty natural that when the EV1 was being developed, that would sort of grow out of the lead acid ecosystem and form the basis for starting us on this electric vehicle journey. So these are examples of EV1 battery modules that you guys will find in the vehicle you're tearing apart. There were 2 different lead acid configurations, and there was also a nickel metal hydride. So lead acid is the kind of battery you would find in your vehicles today, keeping the headlights on and turning over the crank. But the issue with lead acid batteries, as we used them in the EV1, is that they were really heavy. Right. So the battery in the EV1 weighs about 1,300 pounds in lead acid.
And like a 3,000 pound car.
Yes, yeah, it was incredibly heavy.
Yeah.
And it had enough range to go, depending on the model, 80, 90 miles on a charge, but that just wasn't going to be practical to be carrying around that much weight with you for that small of an amount of range. So EV1 started with lead acid, started to transition to a new chemistry that was being used around the late 1990s, early 2000s, which was nickel metal hydride. And those are different metals that are inside the battery that participate in the charging and discharging chemical reactions that let you get work out of it.
So like in a lead battery, if I remember correct, they're all lead plates, but they're separated so the current flows through. Nickel metal, is it all nickel metal plate, or is it different metals side by side?
Yeah, it's a nickel metal hydride, and there's positive anions moving across the electrolyte, so positively charged particles moving across the electrolyte. And batteries are all about a game of opposites attract, okay? So inside the battery, you've got a positive and a negative side, and you have tiny positively charged particles that are moving between the two. And you've got a special feature, which is that electrons, which are negatively charged, can't move through the battery. They have to move outside the battery. So when you're moving those positively charged particles from anode to cathode or cathode to anode, they move through the battery. The electrons move outside the battery to give you electricity to get work done by the battery. So we started with lead acid, put some nickel metal hydride batteries into the EV1, but then at the same time, hybrids were starting to really take off. And so you had nickel metal hydride cells being used in vehicles like the Toyota Prius or the General Motors 2-mode electric hybrid truck or hybrid trucks like the Tahoe and the Yukon and the Escalade.
Anyone who's watched recent videos, I've had 144 of those that I recently discharged, tested, and confirmed were good. So my viewers should recognize that.
Yeah, and the great thing about these is that they were a step along the way to lighter weight, more affordable batteries. But even nickel metal hydride really wasn't going to get us there for lightweight and affordable electric vehicles. And that's where the Chevrolet Volt comes into play as really a bridge to fully electric vehicles. So this is one of the first lithium-ion cells that General Motors put into production for the first generation Volt. And when we replaced these kinds of cells with these kinds of cells, the battery weight dropped from 1,300 pounds to about 400 pounds for the same amount of energy.
Substantial.
Yeah, absolutely. And now you're talking about something where you can actually have efficient vehicle integration. And in the case of the Chevrolet Volt, all that mass that was saved allowed us to put in a gasoline engine and a fuel tank so that vehicle could be electric when you want it and gas when you need it. And you could really go wherever you want.
The range extender, so it
Yes.
took range anxiety out of the picture, because
Absolutely. Yeah, I had one of the, I was really excited. That's sort of where my electric vehicle journey started, because I never had an EV1, but I did have one of the first generation Volts. It was great. We were just talking earlier, I still remember the VIN. It was VIN 3424. I got baby pictures of it being built in the factory from a guy who worked there. And that vehicle was great because over the span of the time that I owned it, I averaged 135 miles per gallon between filling up with gas and charging on electricity. So this really started a journey where when we talk about lithium ion, I said we've got positively charged particles. The lithium is the positively charged particle. So what's great about lithium is it's the third element on the periodic table. So you start off with hydrogen. It's got one proton in the center. Then you run over the other side of the periodic table. You got helium with 2 protons, and then you come back to this side and you've got lithium. So what's great about lithium, it's the first solid at room temperature. There's lots of it in the crust of planet Earth, not battery form. We've got to do work to turn it into battery form, but there's still a lot of it. And because of where it is on the periodic table, it wants to lose that electron. It gives it away to anyone who'll take it. So now you've got 3 protons, 2 electrons. That imbalance makes it positively charged, and now you've got something inside that's tiny, lightweight, ubiquitous, and you can use it to shuttle energy through a battery cell.
So this, when we call it lithium ion, what is the chemistry of this? Is there any extra?
Oh yeah, that's a great question. So the lithium is the thing that's moving energy around, but then you've got an anode and a cathode. All of the anodes that you're going to find on this table in the lithium family, they use graphite for the anode.
Okay.
So graphite is just carbon with certain bonds between the carbon atoms. What's great about graphite is graphite has layers, and those layers are just the right size for lithium ions to wiggle in and out of that lattice.
So it's perfect. Yeah.
It's perfect. And we call that the technical term is intercalation for going in and out of that crystal structure. On the cathode side, there's been an evolution in cathodes as you go from the earliest to the most recent. And that's where you will hear people start talking about those other acronyms, your NMCs, your LFPs. And so what those are, NMC is your nickel, manganese, and cobalt. You'll also hear people talk about NCA, nickel, cobalt, and aluminum. And then LFP is lithium iron phosphate. And these are all different cathode materials that form a structure that's got just the right size between the molecules or the atoms for lithium to get in and out on that side. And they also attract the lithium to them. So what we started off with was little to no nickel in the cells. And that was because we were at the very start of this journey trying to make cells that actually worked.
Right.
And so we started off with a first generation Volt that had 288 cells in it. It had 38 miles of range, and then switched over to gas. So that was a great vehicle to start with. But as we evolved from there, what we always did is we went with the next largest cell that we could manufacture at high quality and integrate into a battery pack. So the second generation Volt, if you heft these 2 cells, you'll notice they're a little bit different in weight. This one's a little bit heavier, right?
A little bit more dense.
Yep, because we cut the number of cells by 1/3. So we went from 288 cells to 192 cells, but we increased range from 38 miles to over 50 miles.
And you still reduce pack weight, or the pack
Yeah.
weight about the same?
Pack weight was a little bit lower.
Okay.
Yeah, still about 400 pounds, but we mostly went after more range. So we held
Right.
weight about the same, went after more range.
And this was the same chemistry makeup, just assembled better?
Slightly more. Now we started to get a little bit of nickel into the chemistry because nickel is really good at attracting and storing those lithium ions, and we were figuring out how we could make it durable. And some of the work that we did, starting on EV1 and in the first generation Volt, about how do you manage thermal system for the battery, how do you manage upper and lower voltage limits, how do you balance cells within the battery pack. All of those kinds of controls and learnings let us go to that next step of how do you put a little bit more energy into the cell.
Yeah, it's better than, rather than starting off with TNT, you're like, how do we manage what we've got? Okay, this is safe, move on a little bit more.
Yeah, you keep taking another step at each time and you figure out how to meet the same level of safety and durability requirements, but doing it with less cost and in a tighter space. So after the second generation Volt, we worked on the first generation Bolt EV, where we started to, this was the first time where we made a cell that had more than 50% nickel in the cathode. So we're marching up on the nickel a little bit, also went with a physically a little bit bigger cell, and we bumped back up to 288 cells. And now we've got a vehicle that goes 230 to 250 miles on a single charge using a lithium ion cell.
And I just love how just the pouch technology is always fun to see and think about that,
There's lots of neat stuff. The pouch is way more high tech than you'd think, and there's actually design features as you go from this generation to our next generation that get the customer more range. So, for example, here, I'll let you hold this cell. If you look at that cell, that's actually a bottom piece and a top piece of foil.
Okay.
And then they've been heat staked around the perimeter and then folded on both sides. You see that?
Yep.
Okay. On this one, we've only got the fold on one side, but not the other side, because this is a single piece of pouch material that wraps around the cell, and then we only have to heat stake on three sides. And this is a really neat feature because the space savings here gives the vehicle about 3 miles extra range.
just from
changing that curl.
I mean, maybe 1/8 of an inch.
Yep. And then what's even better is because we have direct access now to the electrode, we can actually use that edge to glue the cell directly to a cold plate, and we can shift from a design where you had to cool the face of each cell to we just cool the bottom of each cell. And that was another play that made the vehicles more affordable and longer range. And you might think to yourself, oh my goodness, you're not cooling very much of the cell. Here's the trick. The cell has different thermal properties depending on which direction you're conducting. In the plane, it conducts heat about 20 times better than in and out of the plane. So if you're just cooling this face, you got to worry about the temperature on the back face. If you're just cooling the bottom edge, you worry about the temperature on the top. And in balance, those two systems end up being almost the same, just with a lot fewer parts and a lot less cost. And now we have a vehicle that has 288 cells. Yeah.
You hand it over, I was expecting a drop, and it's like,
it's
nope.
a lot thinner. Yeah. So 288 cells, and now we're doing vehicles that go over 330 miles in like a Blazer EV example, or when you put them in a double stacked vehicle like our truck pack, almost 500 miles of range.
Right. It's crazy to think, there's so many of these things in there, so many Capri Suns. Don't put your straw in them. Don't drink your lithium nickel.
Yes, excellent advice. So the last thing I want to talk about now, so this gets you up to where we're at today. We've got one cell going to all our different vehicles in the United States, from an Equinox EV up to an Escalade IQ. And that was a great way to launch our current round of EV products from circa like 2020 to 2025. But as we go forward, we've got enough sales volume in different vehicle segments that we're going to start to offer product that's more tailored for each segment. So that's where Kurt was talking to you about our LMR cells, or lithium manganese rich. I'll talk about that in a minute, but we're going to take chemistries that are more tailored to the application and cell sizes and shapes that are more tailored for the application, like this LMR cell.
A little bit heavier.
It is. It's got more energy in it. So this cell replaces multiple of these cells. what we did with this LMR prismatic cell, we custom made the cell size, we custom made the chemistry that's in it so that it fits perfectly into the bays that are already designed. And now we can take the cell count down by almost 2/3 while still having range of more than 400 miles on a charge.
Right. Which is kind of genius, since you already had that uniform form factor. You're like, all right, well, we have the cases built. A small tweak rather than retooling everything.
Yeah, absolutely. And believe me, we studied everything from complete melt and repour of the entire battery pack and different cell shapes. And when you look at that whole landscape, you basically have a goal-seeking optimization to find, most energy, least mass, least cost. And what we landed on was this is a great structure and foundation to build on. Just drop in cells in a different way.
Right.
So the lithium manganese rich chemistry is really neat. I talked about that march towards more and more nickel for a while. I didn't really explain why. The reason why you want to go with more nickel, it's not just that nickel's really good at holding energy in a battery. It's also that it displaces cobalt. It lets you take the amount of cobalt down, and cobalt is the most expensive material in those cathodes. But we actually got to the point at this stage of the game where you can't take the nickel up much further. But there is another material in the cells, it's that manganese. So now we're kind of looking to do the same sort of swap where we're going to take nickel down and manganese up in order to get more energy in the cell. And you might say, well, why didn't you do that from the start? And the reason is because each of these innovations builds on the last one. Right. And we didn't have the technology or the methods available to us at this stage that we have now.
That's just anything technology, it's progression.
Yes, there's a good example. In the earliest phase of these batteries, the particles inside that are holding on to the material, there's really lots of little grains of material making up the anode and cathode. Those grains were originally homogeneous. They were the same, okay? So the outside of the grain was the same as the inside of the grain. And that's what we could do back then. But when you get to today, what we said is, you know what? The cobalt is really good on the shell of those grains. It fights off some of the reactions on the perimeter, and the nickel's really good in the core for holding on to lithium. So now we've engineered and manufactured new particles that are cobalt-rich shells and nickel-rich cores, and that lets you get that higher nickel, lower cobalt. Where we go from there is we start to innovate on another length scale, where we're not just looking at the shell versus the core, we're actually going inside the layers of the particle, and we're tweaking what materials are inside there with dopants and other materials to make it last longer.
Science, stay in school.
We also have a couple other examples on the table here to talk through. As you guys know, there's several different formats of battery cells. You've got your pouch cells, you've got your prismatic can cells, and cylindrical cells. The reason for all these different types of cells is that batteries are all about layers.
Right.
And we've got, this is where those anodes and cathodes really become real, right? So what we're looking at right here, because it's got a copper foil on it, we know it's an anode because the anode's always going to be on copper. And so that means this is a graphite material. The separator is this white material here. It's kind of like that plastic tooth floss type material. And what's great about it is that lithium ions can go through it, but electrons can't. And if we kept on rolling this, we'd get to the other side, which is aluminum. The reason for these different types of cells is that there's different ways to package up those layers, right? You can roll them up like a roll of paper towel, and you can stick them into a cylinder. You can roll them up and flatten them, and then you can put a flattened roll inside of a can. You'll also find inside of a can, instead of a flattened roll, you'll find a stack. And then inside of a pouch, you'll also find a stack, like a ream of paper.
So that's one of your stacks out of a pouch there, that just piece of aluminum?
This is actually part of, this is part of a cooling system. So this table, we actually interspersed battery cells and some battery module components. So this is actually a super neat part of the first and second generation Volt. This is a liquid thermal cooling plate where these stamped bosses on it make cooling channels that, if you look right there, you can see tiny little channels that took liquid down one side through the plate.
Inside of it?
Yes.
I thought these were channels for it to flow through.
Inside of it.
It actually
Well, so no, I'm glad you picked up on that, because that really speaks to, that's a whole different angle of performance improvements and cost reductions in the thermal space. So thermal learnings that start with EV1 and Volt, transition to Bolt, transition into what we do today.
Andy, this has been amazing. I knew some about batteries, mostly plus to the plus and minus to minus.
You're halfway there.
I'm almost there. I mean, it's bad if you go backwards, ask Billy. It's amazing to just see how far it's come from air-cooled giant bricks to air-cooled and water-cooled bricks again, but it's phenomenal. So thank you so much.
No problem. Thank you for coming. Really excited about what you guys are doing, and I think they're ready for you over at Design.
Awesome. I think I might know what that means.
And we're here at the Mechanical Assembly Lab at the Warren Tech Center and the Design Lab at General Motors. And we're super appreciative that you let us come here today to show us all the great work that you've been doing to help us get 212 back on the road.